Okay, just reviewing a little bit of what we know about the resistance of a circuit or a piece of wire, in this case, to resist flow of current. Our experience is you have a longer piece of nickel chromium wire, you're going to experience less mechanical resistance when cranking the generator, which implies less current because, of course, the mechanical resistance is a reflection of how much current you have. Greater mechanical resistance, more current. Less mechanical resistance, less current. And that implies a greater resistance to the flow of current, since less current means that there's a greater resistance to the flow. Okay, now, a longer wire. What's the effect of the length of a wire on, or why is it that a longer wire has a greater resistance to the flow of current? Longer wire implies that you have a smaller electrical field for a given voltage. Now, I didn't write out all the qualifiers here, but for given voltage, I'll write that here because I can write it small. For given voltage, longer wire, lesser electrical field. Why is that? Well, voltage is equal to your electric field times your distance, so that the electric field is voltage divided by distance or length, and the greater length or greater distance gives you a lesser electric field. Now, why is that important? Because the electric field is what accelerates charges between collisions. Okay? So, smaller electric field means less force on the charges. So, I'll write out here less force. Implies less acceleration of the charges. And by force, I'm talking about force on the free charges. Now, what I mean by collisions, we've seen this. I've shown you the simulation of gas molecules and so forth. The path of your typical charge looks a lot like something like this. Okay, these are straight lines between collisions. This one looks like it curved a little because I just didn't quite get that one right. Wasn't sure where I was going. So the path might look something like this, because the particle doesn't go very far before it collides with another charge, okay, or with it has some interaction with the atoms in the conductor, in the metal in this case. And let's see, I just noticed this one kind of looks curved. Now this would indicate the way the path might look if there's no electric field. Now, if there is an electric field, then instead of a straight line path, which you'd have with no field between collisions, you're going to have a curvature. If the electric field is accelerating your charges in this direction, then you're going to have a parabolic path between collisions. And that parabolic path curved in that direction is going to tend to make the electrons migrate. Okay, so the electrons don't move far, at least not in a short time, or the charges, it could be other than electrons, but the charges don't move far if there's no electric field in a reasonable time. They can migrate, they do a random walk, if you know what a random walk is. If there is a field, then you bias that random walk and you have a drift of your electrons with the field, due to the field. So, this is why a longer wire is going to give you a greater resistance to the flow of charge, because if the wire is longer, you have less electric field, so you have less curvature and a slower migration of charge. Okay, so now we look at two wires of the same length with the same voltage drop. One has a greater cross-sectional area than the other. Which one is going to carry more current? Well, the answer to that is if they have the same length and the same voltage, okay, same length and same voltage, then the electric field is the same in both, because it's only the length and the voltage that determine the electric field. The electric field is the same in both, so all charges in one or the other experience the same force. You have a uniform electric field, same uniform electric field in both. All charges experience the same force. Now, which of these will carry more current? Well, it's going to be the one that has the greater number of charges. If they're the same material, then greater volume is going to imply that there are more charges, and greater volume goes with greater cross-sectional area. And I'm going to make a note here that this is the same material in both cases. So we have the idea that greater length implies lesser electric field, less current, therefore greater resistance. That greater diameter means that there are more charges in any given length that are available, so there are going to be more charges to be drifted past any given point, and that's going to give you greater current. So I could complete this: more current.